Hello, welcome back everybody. Last lecture we discussed the inclusion-exclusion principle. So here is the version that we stated. So collection of big N, distinct objects. Each object satisfies one or more properties. We label those properties A sub 1, A sub 2, and so on out through A sub r. The notation here, we adopted N of A sub I as the number of objects having property A sub I. N of A sub I, A sub j is the number of properties having both properties A sub I and A sub j, and so on. And this principle of inclusion-exclusion, as we saw, was a count on the number of these objects that had none of the properties, which was the total number of objects, minus the sum of number of objects having those each of these properties taken one at a time, plus the sum over number of those properties having number of those objects having the properties A sub I and A sub j taken two at a time, minus the sum over number of objects having properties A sub I, A sub j, A sub k, that is taken three at a time, and so on, alternating in this fashion all the way until you get to this last term, which is minus 1 to the r times the number of objects having all of the properties taken together. Okay, so this is how inclusion-exclusion works. We had a single application of this where we used inclusion-exclusion to count the number of numbers relatively prime to a given number. So this gave us an alternate expression for the Euler phi function, or the totient function, which was doing this counting. Okay, so this is one very nice application of this fact. Let's see some more. So what about the following? This is counting prime numbers. Okay, you might already be aware of various results on various counts on prime numbers. There's famously the prime number theorem, which was proved near the turn of the century, maybe right after late 1800s, maybe late 1800s, early 1900s. I can't remember the exact year, but this was big analytic theorem about the number of primes up to a certain number. That's one more sophisticated treatment of this. We can talk about other methods of counting prime numbers. So here's one particular application of inclusion-exclusion. So first, let's say, so suppose M is composite, meaning it is a number formed by multiplying two or more primes together, but it can at least be written as the product of two integers. So M is AB, where both of these are bigger than 1. But we'll say that, oh, why did I write a comma there? That looks confusing. Let's write it here. So A is strictly bigger than 1, and we'll say that of A and B, B is the larger one. They could, of course, be the same, but we'll take A to be the smaller of the two, if such a thing exists. Then, if this is the case, okay, so both A and B are integers here, but they're bigger than 1. Okay, then what we know is, first of all, A squared is less than or equal to M. Why? So if M can be written as a product of two integers, both larger than 1, take the smaller one of these. If I square that, this is less than or equal to M. Why though? Well, it's just from this, right? So if I take this inequality here and I multiply by a on both sides, a is bigger than 1 here, so I have a squared is less than or equal to a times b, just multiplying both sides of that inequality by a, but a times b is equal to m. So a squared is definitely less than or equal to m in this case. Square root's an increasing function though, so obviously this leads to the following estimate, that a must be less than or equal to the square root of m. What does this say? Means that since m is composite, then m must be divisible by a prime p such that p is less than or equal to the square root of m. So this would be, you know, if you were thinking of running, right, a program to check divisibility of a number by primes, right? If you were doing like the most brute force like thing that you'd put like the least amount of thought in, right? You're literally just checking every single number smaller than m, right? If you want to answer whether or not a number is prime, right? Whether it's divisible by any of the primes that come before it. So this is telling you that there's no need to do that, right? This is improving the runtime of your code significantly, right? You're like improving it by like a square root factor here. You only have to check up to the square root of m. You don't need to check up to all of m. So it's telling you that if the thing is divisible by prime, it's got to be divisible by a prime that's less than or equal to its square root. So this is cutting off a chunk of numbers that you don't have to check now if you're just looking for any divisibility whatsoever. So that's nice. So using this together with inclusion-exclusion, we can count the number of primes between 1 and a given positive integer. So the idea, use this plus inclusion-exclusion to count the number of primes between 1 and a given positive integer n. So how do we go about doing this, right? So let's start with the set containing the positive integers 1 to n. Okay, and so I want to use this theorem to count the number of elements that remain when multiples of prime numbers p less than or equal to the square root of n are excluded from the set. So I want to count the number of elements of the set that remain when multiples of primes p that are less than or equal to the square root of n are excluded from the set. Or deleted from the set. Okay. Well, since any composite number by this first fact has some prime that divides it that satisfies this, excluding all these numbers removes all the composite numbers from the set, right? So So this should remove all composite numbers from the set. Meaning what is left behind should just be all the primes up to n. So we can count that set that is left behind, and that will give us the exact count that we want. Okay. Okay. So how nice is this in terms of how does this improvement help us? Well, for instance, well, let's do this for, I'm going to choose n equals 120. So quick example here, if n is equal to 120, then the largest prime less than or equal to square root of 120 is, so less than or equal to square root of 120, so this is numbers like 10 and less, right? So 7 is going to be the largest such prime. Okay. So I need to exclude all of the composite numbers. So to exclude all composites in the set 1, 2, up to 120, I only need 4 properties. The 4 properties come from a count on the previous primes. So because this is small, I know the primes up to 7, right? So I know 2, 3, 5, and 7, but those are exactly the 4 properties that we need. So what are the 4 properties? So a sub 1 is the property is divisible by 2. Of course, you might notice, of course, being divisible by 2 just means you're even, so you could write that as just being even. A sub 2 is divisible by 3. A sub 3 is divisible by 5. And a sub 4 is divisible by 7. Okay. So then we can actually just compute what is the number of these integers 1 to 120 divisible by 2. Well, exactly half of them, right? So this is 120 over 2, or 60. What about those divisible by 3? Well, this is exactly a third of them, right? These are the multiples of 3 that we're excluding, so there's 40 of those. What about the number divisible by 5? Well, this is 120 divided by 5, which is 24. And what about the last divisible by 7? You might say, well, clearly this is 120 divided by 7, but you immediately see, oh wait, that doesn't make any sense. It's 120 divided by 7. This is not a positive integer, right? This is some, like, this is not integral, right? This is not an integer. So how do I fix this count? Well, using the floor function works fine. And there are 24 such things. Okay. So this is a use for our floor function here. Okay. So that's the count of all the properties taken one at a time. What about these things taken two at a time? So for instance, like, how does this work? So these would be numbers divisible by 2 and 3. So, well, we could always just slap this floor function on them because we were able to see, of course, obviously, that these were all divisible by 2, 3, and 5 here. So when we got to 7, we weren't. But if you just want to be safe, right, and going forward here so that you don't have to think about whether or not, you know, this thing is an integer or not, you could always just slap the floor of the quantity on here. So here, this would be 120 over 2 times 3. This is 120 over 6, which of course is 20. What about divisible by 2 and divisible by 5? This would be 120 over 2 times 5, so over 10. Of course, that's 12. Okay. And we can keep doing this until we exhaust all things in this manner. If we want to see how this computation works out, we could say, well, using inclusion-exclusion, this number of objects satisfying none of the properties, this should be all of the primes, right? So this is going to be the total number of objects, of which there's 120. So there's 120 total numbers, positive integers between 1 and 20, or 1 and 120, sorry. So this is 120 minus the sum of these things taken one at a time. We've computed all of these, so this would be 60 plus 40 plus 24 plus 24. Okay. Plus the sum of these taken two at a time. We computed a couple of these, but if we want to go all the way, this would be 20 plus 12 plus 8 plus 8 plus 5 plus 3. Okay, we subtract from that these taken 3 at a time. We didn't compute any of those here. You can do that very quickly. There's only 4 things you have to compute. So this would be 4 plus 2 plus 1 plus 1 plus the number of these taken 4 at a time. So that's divisible by 2, 3, 5, and 7. So that is 2, 3, 5, and 7. That's not going to be possible. It's going to be greater than 120. So there's exactly 0 ways for that to happen. Which, if you carry this out, this is 27. Okay. But here's the thing. You might say, are we done? Well, what did we count? We tossed away the numbers. So what did we toss away here? We tossed away multiples of 2, 3, 5, and 7, and also multiples of combos of these things. So, of course, it's just multiples of 2, 3, 5, and 7. But that includes 2, 3, 5, and 7 themselves, all of which are primes. So I want to add those back in, right? Also, a number that doesn't get excluded is 1, which is not a prime, right? For reasons that make the statement of various theorems extremely awkward if you were to define 1 to be a prime. 1 is not a prime, just because it makes the statements of theorems involving primes way, way simpler if 1 is not a prime. So 1 is not a prime, but that gets included here because 1 is neither divisible by any of these things, so 1 would be included. So we need to remove 1 here. So total number of primes between 1 and 120 is equal to this n naught here that we have computed, plus 4 that adds in the primes 2, 3, 5, and 7 that we had excluded, and 1 to get rid of 1, because 1 is included in this count and we don't want it to be. So we have to modify this slightly. So this is n naught plus 3, 27 plus 3, so there's 30 of these primes. Now, the reason why this example is nice is because it shows a couple of things. One, just because you're primarily using the inclusion-exclusion principle to do some bit of counting, doesn't mean you're not going to have to slightly adjust it. So what I mean is that when you use inclusion-exclusion, there's no rule saying that you have to be done in one step. You apply inclusion-exclusion and you're just done and that's it. That's not necessarily how it will work. Maybe you use inclusion-exclusion to get a count of one thing. You might have to use it for something else in the same problem to get a count of another thing. Or you may find that it's most convenient to organize this info, say, in this way, but obviously this isn't perfect because we excluded some primes we wanted to count and we also included a number we didn't want to count. But because there's only, 4 primes and then the extra number 1, that's something we can easily take care of at the end, right? And so oftentimes that's exactly how your counting process is going to work. It is going to be done exactly in this way. Where you have to make some mild adjustments on things depending on how you had to define these properties. So that's just something to that you're going to have to look for. So this is a very standard application of inclusion-exclusion stuff. So this is this is something you will likely need to do in homeworks involving this, for instance. Okay. Let's see another example of using this for chromatic polynomials. So we, of course, saw how to deduce chromatic polynomials using a theorem that allowed us to break these down using the operations of edge deletion as well as this edge collapsing mod operation that we defined. So you can go back and look. I can't remember off the top of my head what video number that is, but if you look for it will be the lecture on chromatic polynomials has that application. But because necessarily the chromatic polynomials are telling you something about a count of things, right? So we could think about how to generate these with a counting argument. And so if we let G be a graph, recall that the chromatic polynomial of G in variable x is the number of ways to color the vertices of G using at most x colors in such a way that no two vertices connected by an edge have the same color, right? That was what this was. This was the number of ways to color G. Remember, this is vertex coloring, not edge coloring, so this is a vertex coloring. Number of ways to color G using at most X colors in such a way that no two adjacent vertices have the same color. This is just, instead of calling this a proper X coloring or something, I'm just writing out in words exactly what that means. Okay, so that no two adjacent vertices are colored the same color. Okay, so we can use inclusion-exclusion to count this. So we can use inclusion-exclusion to count this. But how do we do this with properties, right? So let's say that the order of G is n, so it has n vertices. Okay, if we look at so consider set of colorings of vertices of G using at most X colors, then in this case, if I have a set of colorings of vertices using at most X colors, if this is my set of big N objects, then big N is exactly X to the little n. All right. Now, to find the chromatic polynomial of G in X, we got to exclude all of the inadmissible colorings from this set. Inadmissible colorings from this set. But what is an inadmissible coloring? Well, it's a coloring where there exists a pair of adjacent vertices that have the same color, right? So, for each edge E sub I in the graph G, let the property A sub I be the following. A sub I is edge E sub I connects two vertices that have the same color. Okay. So edge E sub I connects two vertices having the same color. Now, why is this the property I pick for each eye? Well, what if an object in my set doesn't satisfy any combo of such properties? Well, then it would be an object that is definitely not an inadmissible coloring. That is, it would be an admissible coloring strictly. It would be a proper coloring, which is exactly the thing I'm trying to count with the chromatic polynomial, right? So no adjacent vertices have the same color. So an object that satisfies none of these properties is one that is not an inadmissible coloring. It's a proper coloring. Okay. So, saying what I just said in words is to say that the number of objects satisfying none of these properties is exactly the chromatic polynomial, okay, of G. Okay. So, what would this be like if, for instance, G was something fairly simple? We'll take like K3, for instance. So let's use this in the example that, actually, let's just do it right here. We got enough room. Let's say G is the complete graph on 3 vertices. Okay, so let's see how this works here. What is this? So by symmetry, all these are going to be the same. So that is, what is the number of objects having one of these properties? That is, A sub 1 is edge E1 connects the 2 vertices having the same color. Edge E2 connects 2 vertices having the same color. Edge E3 connects 2 vertices having the same color. So how many? I have 3 edges, right? If I draw K3 here. So here's E1, E2, and E3. Well, any coloring satisfying one of these properties has 2 vertices of the same color. I used X colors, so this is X squared in all cases. All right? And again, this is because every coloring that satisfies one of the properties has 2 vertices with the same color, and the third vertex can be whatever color. So that's why this is X squared. What about these taken 2 at a time? Well, so A1, A2, A2, A3, A1, A3. And in fact, even taken all together, all of these are what? Well, here this would be edge 1 connects 2 vertices having the same color. Edge 2 connects 2 vertices having the same color. But if these 2 vertices have the same color and these 2 vertices have the same color, then all vertices have the same color in this case. Similarly, for A2 and A3, this would be E2 connecting 2 vertices of the same color, so then these 2 vertices have the same color, and E3 connecting 2 vertices of the same color. So again, we get all 3 vertices having the same color. Obviously, in A1, A2, A3, we have all 3 vertices having the same color. Same in this case. So this is all 3 vertices having the same color in each case. And the number of those colorings is X. Okay. Why? Well, again, if you're using X colors, then you could color them all red, blue, green, whatever, however many colors you have, that's how many different colorings you have that satisfy these properties. Right? In the previous case, because 2 vertices are colored one color and the other vertex is colored whatever color, using X colors, you have X squared ways of doing this, again, because you're using 2 colors in any case. Okay. Okay. So this is everything. This is all we need. So then what is my chromatic polynomial? This is, of course, my N naught in inclusion-exclusion principle. So according to this, just using inclusion-exclusion, this would be big N, which is x cubed, minus the sum of these identical elements, so x squared plus x squared plus x squared, so this would be minus 3x squared, plus the sum of the three terms taken two at a time, all of which are x, so this would be plus 3x minus x, which is the last term. And so, actually, rewriting this, factoring, this is x times x minus 1 times x minus 2, which could be also realized as x to the 3 falling. Repeat this for case of 4. All right, repeat this for case of 4. And see if you can generate the chromatic polynomial in that fashion. All right, compare this to what we did when we actually did the chromatic polynomial back a week and a half or so ago. Okay. So one more. We'll apply this to what we'll call derangements. Okay, so what is the setup? The setup here is the following problem. Suppose a lazy professor gives a quiz to a class of n students, then collects the papers, shuffles them, and redistributes them randomly to the class for grading. Obviously, even though the professor's lazy, there's some minimum amount of care here to not be too unfair. So the professor wants to make it in such a way that no student receives his or her own paper to grade. So class of n students, take quiz, shuffle papers, and redistribute. What is probability that no student receives their own paper? I went to a Magic the Gathering tournament once when I was like, I think I was like 14. It was in 1999. It was a junior, no, it wasn't Junior Super Series. It was some kind of big draft thing. Yeah, so it was a draft tournament. Doesn't matter if you don't know what that is. Point is that as part of the way that this works, you get a actually no, it wasn't draft. It was sealed deck. Okay, all right, sealed deck, fine, whatever. So you get this. You get the sealed deck of cards. The cards you get and the packs included are random. You have to categorize them. You classify the ones that you get when you get sent the cards, and then that list and the decks are reassembled and given back to the tournament organizers, which then redistribute them to the actual people that are going to play them in the tournament. Everybody gets a different deck. But of course, you could get the deck uh, that you yourself like organized and marked off, inventoried, basically. Although most people are not. Most people are going to get a deck back that's different. And so what happened was I didn't know how this process worked. I was 14. I'd never been to a tournament like this, so I had no idea what was going on. I thought that I only had that time to actually like organize my deck and build my deck. So on the paper, there was a slot for name of player, and then there's a slot for the name of person who received the deck after the person had like organized it. Basically, I thought that was weird, so I just put my name in both slots and kept going. Well, anyway, um, at the at the end of this process, a couple of people received their own decks that they had organized. I was one of them, but when they read it off, because I'd put my name in both slots, they were like, person receiving their deck this time is they can see the future because, well, they have written their name in both slots, so they knew they were going to be selected to get their own deck back. And it was very funny, and everybody laughed. And that is exactly ending up in this situation of being someone that does get their own paper back in this instance, and having some fake foreknowledge of it. This sort of thing, a permutation of some number of objects in this way so that none of the objects shares their original position, if you like, is called a derangement. So I'll write that down in a second. But we have some other questions, right? So here's second question. So maybe if you call this question 1, question 2, is this probability significantly different depending on class size? Which leads to a very related third question you could even group in with the second question, which is what is the limiting probability as n goes to infinity? Okay. So, this is all these are valid questions. The thing is that as this n gets bigger and bigger, of course, there's more ways for at least one person to get their own paper back, right? So, who like it's hard to say just looking at it like this without actually writing down the math, like how this is going to affect, this total number of permutations possible. And so this leads us to the following definition, which is we have n objects in what we'll call initial configuration. Because oftentimes this is more what you're worried about. In objects in initial configuration, a permutation of these objects in which the position of each object differs from its initial position is called a derangement of the objects. Okay. So a permutation of these objects in which the position of each object differs from its initial position is called a derangement of the n objects. We denote the number of such derangements as ingnab. You don't have to call it that. This is just the number of derangements. So it is an upside down exclamation mark. Okay. The joke being made in the text is that if people call, if you might call the in factorial symbol in bang, because it's an exclamation mark, you could call this one in gnab, where you've spelled bang backward. But this is the number of derangements of in objects. Okay. And so this is what I'm actually interested in computing here. So let's do this for small numbers of objects here. So what about the number of derangements of, say, 0 objects? Well, here there's nothing. It vacuously satisfies the derangement condition since there's no object, so it vacuously matches the position, or doesn't match its initial position because there's nothing to match here. So this is 1. Okay. But here's something a little weird. What is the number of derangements of a single object? Well, for a single object, there's only a single permutation, but that permutation fixes that single object, right? So there's no other permutation, right? There is no arrangement of that one object that differs from its initial position. So the number of derangements of a single object is actually 0, because it's impossible to permute the objects in a way that doesn't displace, or sorry, that does displace the object, or leaves it in a position other than its original position. Okay. What about so this is when n is equal to 2. What is, I know these start to look like j's. What is this? Well, you have 2 objects. If you fix both objects in their initial position, that's not a derangement. If you interchange them, if you swap them, that is a derangement, and that's the only one, right? So that's 1. Okay. What about when n is equal to 3? So what is this? You have permutations on 3 objects. You can't fix any of the objects, right? So if the objects are labeled, say 1, 2, 3, right? If I were to swap any 2 of them, that's no good because that leaves fixed the 3rd. So that's no good. So then what am I allowed to do? I could shift all of them 1. So I could shift, say, to the left. 3 comes over here. So 1, 2, 3. I'm not going to use cycle notation, although that would make this way easier. Cycle notation is like an extra skill you've got to develop. Maybe you know it from taking an algebra course or whatever. Maybe you don't, so it's fine. I'm not gonna use it, but if you know cycle notation to deal with permutations, that's perfectly fine. You can use that, but I'm not gonna expect you all to brush up on that separately. So I'm just gonna write it in somewhat cumbersome notation here. So this is like something that swaps any two of these is not going to work because it's going to leave the third one fixed. So then what do I need? If the original arrangement, I'll use square brackets here because that's what the text does. So then what can I do? I can do this. I can do this, as I was saying. I can shift in this way, but that's it, right? Any of the swaps is not going to work because I can't fix anything here in a derangement. So this is the initial position. I get these two derangements and nothing else, right? Try anything else here. It's going to fix something. So this is actually 2. Okay. Well, let's do one more. So we're looking for number of derangements for objects. Again, if I have an initial position or initial configuration, 1, 2, 3, 4 in this way, what do I get here? Well, here I have plenty. So I can do several shifts and I can also do double swaps now. So what do I mean by that? Here, I couldn't do double swaps because there weren't two extra elements to swap at the same time, right? So I couldn't swap 2 and 3 and simultaneously swap 1 to something else because there is no something else. So that's why swaps weren't allowed here, right? So I couldn't swap these things, okay? But I could do this shift, right? So I could put the 3 goes over here, and then 3, 1, 2, or pushing it back this way, pushing it to the left, 2, 3, 1. That's fine. Or 2 shifts in the same direction, 3, 1, 2, and then 2, 3, 1. Here, what can I do? I could swap 1 and 2 and 3 and 4 at the same time, right, to get this. Right, that's fine. Okay, that's an example of something that I can do. I could also do, and of course you could swap the things you're swapping here. So I could swap the inner 2 and outer 2. So this would be 4, 3, 2, 1. I could also shift to the right. So this would be 4, 1, 2, 3. I could also shift again to the right. So this would be 3, 4, 1, 2. I could shift again to the right. So this would be 2, 3, 4, 1. I could shift to the left, which would be 2, 3, 4, 1. That's fine. I can shift to the left again, which would be 3, 4, 3, 4, 1, 2. So 3, 4, 1, 2 I've already gotten here. So shifting all in one way, shifting in the other way, these are going to be the same thing here. So I've already counted those. I could think now about swapping some of these other things. I want you to keep going here to write out the remainder, but there are 8 total. Okay. Okay, or rather, did I count them all? Let me see here. See if I actually counted all of them. I may have. No, there's 9 total. I missed one. All right, 9 total. This is 9. Okay. And so, returning to our question, what is the probability that no student receives their own paper? The answer for n equals 0, 1, 2, 3, and 4 is just going respectively here 100% in the n equals 0 case, 0% in the n equals 1 case. It's 1/2 in the n equals 2 case. It is 1/3 in the n equals 3 case, and it is 3/8 in the n equals 4 case. Okay. And so this is kind of like our first example of trying to see what we think this probability is approaching. Okay, you might already have some ideas here. You could try this if you wanted to try to compute this. I wouldn't do it brute force in this way, or you could look up what these numbers are to see what some of these probabilities would be. But let's do this more generally for general n here. So I want to use inclusion-exclusion. That's the point. How? So how do I do this? Well, I'm going to select the original set to be the collection of all permutations of the n objects and for I between 1 and n, let a sub I be the property that element I remains in its original position in a permutation. Element I remains in its original position in a permutation. Then this n naught, which is the number of objects satisfying none of these properties, is the number of permutations that contain no element that remains in its original position, i.e. this is just all the derangements. Right, so this is the number of permutations where no elements remain in their original position. But this is just the number of derangements. Okay. Now, you might say, oh, this might be kind of nasty to deal with. But in fact, because of their relationship to permutations and because we know how to count permutations, this is not so bad. This is actually extremely amenable to all the tools we have right now. And so, what do we do? So, Let's compute this thing for a single property, a sub I. So notice, first of all, that the number of permutations satisfying this property, that is, element I remains in its original position, are actually n minus 1 factorial. Why? This is because element I is fixed, but all other elements may be permuted arbitrarily. And we know how to talk about the number of permutations on some list of objects. If n is the total number of objects, then permutations on n objects is n factorial. But since one of the objects is fixed, the remaining elements, of which there are n minus 1, can be permuted arbitrarily. There are n minus 1 factorial such permutations. So there it is. Okay. Similarly, if I talk about the properties taken 2 at a time, then 2 elements are fixed, and the rest may be permuted arbitrarily. So this is n minus 2 factorial. Okay, and this is for I less than j. And taken 3 at a time, again, the same reasoning. Now you have 3 elements fixed, but the rest are permuted arbitrarily. There are n minus 3 factorial such permutations, and this is for I less than j less than k, and so on, so that the number of derangements of n objects is n factorial. That's the total number of objects, that's big N, minus the sum over I of n minus 1 factorial plus the sum over I less than j, n minus 2 factorial, minus, and so on. Your generic term is plus minus 1 to the m times the sum over I1 less than I2, and so on out to less than Im of n minus m factorial plus, and so on, the final term, minus 1 to the n times, this is going to be n minus n factorial. 0 factorial is just going to be 1. There's going to be a single term in this thing. This does it. Okay. But actually, what is the count here on this generic, the number of m tuples I1 to Im that satisfy this, right? So what is the number of such m tuples? This is just the number of ways to choose m from n objects. This is just n choose m. And so, in each of these terms, we actually know exactly how the sum goes, right? So this thing, remember, this is just this single coefficient in this sum. So this is n factorial minus n choose 1 times n minus 1 factorial. Now, you might have noticed, right, that here I'm summing over I. What does that even mean? This is the number of ways to choose a single index from n indices. There's n such ways, but just to nail down what it is that's happening here, this would be n choose 1. We know this is n. That's fine. There's n ways to choose one object from n. That's us recognizing there are n terms in the sum. each term is an identical copy of n minus 1 factorial. And again, that's because how many ways are there to choose these things one at a time from n? Well, there's n of those ways, right? Because there are n objects, there are n indices here. I goes from 1 to n. I'm going to get a copy of these for every single one of those, so 1 to n of those. N choose 1. Okay, plus, taking 2 at a time, I'm summing over I less than j, so this is how can I choose two indices, I and j, with I less than j, from n total? Well, that's n choose 2. Times n minus 2 factorial. And so on, minus, plus your generic term is minus 1 to the m times n choose m times n minus m factorial, and so on, all the way to minus 1 to the n. And so rewriting this in a clever way using sum notation, this would be the sum over m of 1 minus n to the m, n choose m, times n minus m factorial. Okay. Now let's stop for a second. You might have a couple of complaints here. You might say, what happened to the n factorial? That's included here in the m equals 0 term. When m is equal to 0, this is minus 1 to the 0, so that's just 1. N choose 0, that's 1. N minus 0 factorial is n factorial. So the m equals 0 term in the sum is n factorial. When m is equal to 1, this is minus 1 times n choose 1 times n minus 1 factorial. That's the, here is the m equals 0 term, here's the m equals 1 term. You can check that this is indeed the m equals 2 term, and so on. And then this is the m equals n term. Okay. So this is what I get. Of course, there's an even better way of writing this. We can combine this very nicely here using, so how can you write this more conveniently? Well, n choose m, of course, we know exactly what that looks like. That's n factorial over m factorial times n minus m factorial. So maybe here, I'll do it as one step. These cancel. N factorial does not depend on this this m at all. So this is n factorial times the sum over m of minus 1 to the m times 1 over m factorial. So what was this, of course? This was the number of derangements, right? Thus, if I want to talk about the probability of no student getting their paper, right? So hold on real quick. Let's move on so that I can rewrite this again. So question. What is probability of a derangement? The probability that a permutation of n objects is a derangement. Well, this would be number of derangements over number of permutations. but this is the number of derangements divided by n factorial. But the number of derangements we found to be this expression. Here, I'll leave that on the page here. So this is n factorial times the sum over m of, I'm going to write it as minus 1 to the m over m factorial divided by n factorial. The n factorials cancel, and so this probability is the sum over m of 1 to the m, or sorry, minus 1 to the m over m factorial. And this is a sum from m equals 0 to n. That is our probability. So this fully answers the question of probability. The question, what is this in the limit? Well, that is, what is the limit as n goes to infinity of the number of derangements over the number of permutations? Sorry. Well, this is the limit as n goes to infinity of the sum from m equals 0 to n minus 1 to the m over m factorial. That is, this is a sum. We have another way of writing this, of course. This is the sum from m equals 0 to infinity of minus 1 to the m over m factorial. Could someone tell me what that is? You know what this is. Recall. The most important function in all of mathematics. You can define it this way, actually, or you can define it using logarithms, and you can do that if you want to. Define it as the inverse to the natural log. That's perfectly fine, which in itself is essentially defining it as a solution to a certain differential equation. If we don't care about that, right, if we don't use like fundamental theorem of calculus to do it, you can also just formally define it to be the following power series. So this is the sum from m equals 0 to infinity of x to the m over m factorial. This is what e to the x is. And thus, I recognize this is e to the minus 1. This is 1 over e. That is, this is like 36.8%. So, you got about a 36.8% chance that what you get is a derangement if you got a very large class, right? So, for a sizable enough class, this is what you got. All right, so that is, I like this example for a number of reasons. One, this leads us nicely into, at least superficially leads us nicely into kind of the next thing I want to talk about, which is relating counting to series like this. But also this brings in like an analytic part to this, where we are using the fact that we recognize a sum like this to answer questions about this limit. Of course, when a limit is entering in, it shouldn't be that surprising that there's some analytical stuff going on, hiding in the background. But this is a nice example to kind of show, to fully illustrate all of the overlaps here. So this was quite a lot we managed to do with inclusion-exclusion. There's a wide variety of applications, and you're going to see in your next homework kind of how you can use this. Okay. So now, just because I mentioned it ever so slightly, I only have a couple minutes left, so I'm just going to use this to define my term. This is the notion of a generating function. So what is a generating function? So given a sequence, we'll call it a sub k with k greater than or equal to 0. Its generating function g of x is defined by the following. This is the sum over k non-negative of a sub k x to the k. Note, if the sequence in question is finite, this g of x is a polynomial. If this sequence is infinite, well, g of x is then an infinite degree polynomial, which we have another name for, which is its power series. Okay. So examples, real quick. If we'll say a sub k is minus 1 to the k over k factorial, then g of x is the Maclaurin series, that is centered around 0 of e to the minus x. If a sub k is, say, n choose k, where n is some fixed non-negative integer, then g of x is simply 1 plus x to the n, and this is by the binomial theorem. All right, think about this. All right, in terms of this definition, this is just g of x in this case would be the sum, or k greater than or equal to 0 of n choose k, x to the k. That is, of course, equal to n choose k x to the k times 1 to the n minus k by the binomial theorem. This is 1 plus x to the n. This is what our g of x is. Okay. Now, the question that you might have is, how can I use this to solve combinatorial problems? And the answer, you'll have to wait till next time. So next time you will get to see an example of using this to solve combinatorial problems. Okay. We are going to spend the next couple of lectures talking about, I don't think I'll be able to finish it all in a single lecture, so I think we're going to spend the next couple of lectures talking about various applications of generating functions. We won't be able to fully exhaust it, but these have wide range of applications in a variety of settings, so we're going to see plenty of them before moving on. So you are going to be seeing a lot of generating functions, so you will get used to these very soon. But I think that's all that I have time for today. So I'm going to stop the stream and I'll restart it for a problem session for your homework that is due tonight. So in case you have any questions. So anyway, I think that is all for today. So I will see you all tomorrow.